I despise Frank Ocean, everything that he's ever made or thought about. Yeah, personal feelings, I don't know. All right, so here we are. We are continuing on. We have knocked out addition. We didn't really do it, but we talked about subtraction. At least it's the same as addition. Just be careful with the negative. And we talked about multiplication. There's only one little step of arithmetic left. Division. So check it out. Instead of just jumping in and saying, hey, here's an example with it, our whole piece so far has just been complex, the imaginary unit, and then we're looking at arithmetic in C. Now, when we're looking at this, Matilda, just in case you want to use a shorthand, this is what is called the Blackboard C, just like this is a Blackboard R. This is the complex numbers. They all have the form A plus BI, every single one of them. Okay, so within our arithmetic section, it's going to feel like it's kind of sneaking out of nowhere, but we're going to define for ourselves our complex conjugate. Complex conjugates. Now, you guys have seen conjugates with radical stuff. I'm certain we will see them again. Are you allowed to keep radicals in the denominator of a fraction?
No.
So there's no real reason to it other than it makes the unit circle nicer. After this year, you'll never have to do that again, unless you're on the unit circle, because we all learn it that way. Okay, for this, we need a way to clean up when we divide by an imaginary number all the same. So here's what we're going to do. We're just going to give ourselves a nice definition right off the bat, and then we'll see the utility of it. And we've actually already seen the value in this. Given a complex number, A plus BI. And I'm going to suggest we add 1 mark to this afterward. You won't have to erase anything. We'll just start here, though. Given A plus BI, its conjugate is, and we would say it's its complex conjugate, but it's implied that we're in the complex numbers right now. Its conjugate is A minus BI. That's it. Now, here's my suggestion, and it's a weird one to do. Could I make this plus or minus? Like, can I add a minus sign here? And I'll even change color so it stands out. If I do this, it's trying to save some time. We're going to see something. I don't know if you've seen it before, but it's common in math, kind of at least. If it's A plus BI, its conjugate is A minus BI. But is it possible that I give you A minus BI first? And what's its conjugate? A plus, right? We just switched the sign in the middle. This is weird. I don't know if you've ever seen it, but you're okay with plus or minus. Have you ever dealt with minus or plus?
Yeah. Sure.
Like, have you ever written it?
No.
Now, it looks odd, right? And you're going to say, well, it's the same thing in the end. Kind of. It is the same, but it's much more specific. Top to top, bottom to bottom. And what I mean by that is right now, if I take A plus BI, do we agree that the plus on the first one is on top? Mm-hmm. Its conjugate is A minus. It's the top again. If we do A minus BI, its conjugate is the bottom one now, A plus. It happens. We'll see it again in some trig stuff. Anybody opposed to using this rather than writing the exact same statement? Again, just with the order changed. Okay, so the value of these and why we care about this in complex conjugates, and I'm going to write, we'll switch back to the same blue, I think it's that one, the follow-up little comment with it. We can escape the complex numbers, kind of. So we always get a real number when multiplying by conjugates. Every time. And I'm going to say complex conjugates. We're going to use the Blackboard C. Complex. You know what? I kind of like this. Complex conjugates. Okay, and we saw this yesterday and we used it, and I think that most people, based on the 5-second problems that I gave us a minute ago, you have it, but I want to write it down one more time. If I do A minus BI times its conjugate, A plus BI, is there a fast, easy, efficient way to get this? What is it, Olin? A squared plus B squared. Because the middle pieces always fall out. That's what happens when we FOIL the difference of two squares. Okay. Now, We use this all over the place. And the easiest, like whether it's with complex numbers or not, the idea of a conjugate, we'll see it again. I guarantee you'll see it again. With regard to complex conjugates, we use this when we do division because just like radical stuff, we don't want to keep imaginary values in our denominator, ever. We get rid of them, which means when we actually divide, all we're doing, we're not actually getting a quotient necessarily, but we are simply cleaning it up and making the denominator completely real. Like that's the goal here. Okay, any questions here before we just jump right into dividing? Okay, so let's go ahead and do that. Our last little piece, we're going to do an example, and I'm going to put a little bit of front knowledge, I don't know how to word this, a preface, if you will, with division in the complex numbers. Okay, where everything gets kind of weird with this is you've been in the complex numbers your whole life, it's just the value of b has always been 0. Like, we're still in the complexes, so nothing crazy different happens, but we do have to think about it when we change this. Okay, only comment I'm going to make. If we're doing division in the complex numbers, we make the denominator real. That's it. That's our goal. We're essentially just simplifying when we do division. So here we go. Let's knock out a couple of them. And for my first trick, we're going to say we get this lovely division. 2 plus I over, I don't know, 3 minus 5i. Okay. I don't normally start the problem right here, but I think it's a natural place to begin. If you guys don't color code, that's okay. Do you have a way to indicate that this is what we started with if I immediately start doing new stuff? Okay. I wouldn't, you do you. Your notes are your notes. That's fine. Okay. Right now, do I have imaginary parts on this number? Are there any in the denominator? Well, shucks. How do we get rid of them? Let's multiply by the conjugate. Now, be careful because you're right in the end, but the language, if all you tell me is to multiply by the conjugate, I'm going to be like the devil's advocate right now. Here's the conjugate. I've done it.
No, the conjugate over the conjugate.
Oh, so we're going to use the conjugate to come up with a clever choice of 1.
Yeah.
Perfect. I'm good with that. And I know that that's what you meant. I just want to like really demonstrate that language, the clarity. Those were different statements. So if I multiply by the conjugate in the numerator and the conjugate in the denominator, 3 plus 5i over 3 plus 5i, what am I really multiplying by?
We switch the numbers, or we just change the sign.
Just that one. So instead of 3 minus, if we look back, and you should look at yours to verify that we have it, the conjugate of a plus bi is a minus bi. Only the sign in the middle changes. Okay. Now, when we're doing this, the bottom is easy, and my hope is that the bottom part of this is easy without anything crazy extra. Can you guys tell me what the denominator is?
34.
9, 3 squared plus 5 squared, 9 plus 25, it is 34. Now, if you're looking at this and going, I don't know how you did that, it's an exact a minus bi and an a plus bi, a squared plus b squared. We're just going to use that. The top, can we do it quite as fast? Not quite. Like, we're close. Some of you can probably do it all in your head. I'm going to show not every single individual step, but we will talk about them all. I'm going to use the F word.
Foil.
Indeed. It's one of those. It's FOIL here. And really it's distribute, but I'm okay with that. 2 times 3 is?
6.
And I'm going to, here's my little bit of work I'm going to save. I'm going to put this in my back pocket here in a minute. What's 2 times 5i?
10.
10i. I'm going to put that in my pocket for now. I times 3?
3i.
So we had 10i plus 3i?
13i.
13i in the end. And then I'm going to actually write this one. I times 5i plus 5i squared. Okay. So there's a few things that are going to happen here. And I'm always in favor of showing less work unless you make mistakes when you do that, in which case show more work, which is like the exact opposite of that statement. Okay. I'm going to make a little note here. If I think of 5i squared, this is equal to 5 times I squared is -1, which is equal to -5. This right here is a -5. I just haven't written it that way. If you want to do it in one line, cool. I'm going to write it in two with this work just done here. The numerator then becomes 6 plus 13i minus 5 all over 34. Totally up to you if you want to write this step or not, because I think that it's reasonable that most people in here can probably omit this one. When I combine any and all of my like terms, what do I get? 1 plus 13i over 34. Now, in all reality, I'm fine with this answer. I'm good with it. It looks good to me. More commonly, especially on the AP test when we get there, and we'll start doing our practice AP stuff here before too terribly long. We want to write numbers. They all have, complex numbers all have a very particular form. What does every complex number look like? A plus bi. Right here I have a plus bi over something. Can we make it so it's just one number a real part, plus just the imaginary part?
Yes.
In other words, can I split this fraction?
Yes.
How do I split this fraction? I can split a numerator, I can't split denominators. How can I rewrite this? So you say times 34, but we got to be really careful because I don't have two sides of an equation. I can't use properties of equality here.
1/34.
It is exactly 1 over 34 plus, and I don't care how you write this one. You might write 13/34 I. I prefer to write it here. Either way is cool with me. Okay. On my test, I'm okay with either. On the AP test, this is going to be what they're after. Okay, this is what's called a complex number in standard form, where it's very explicitly a plus bi. They're the same answer, just moved. Everybody okay with that? Okay, I want you to do one more of these, and I guess we can probably do democracy. Do we need one more like this, or do you want to move on to the next type of problem?
One more.
One more, deal. I want you guys, I'm going to throw you for a loop here. 3, we'll say 3 plus I, I'm sorry, over 2i. Cool. It looks different. It feels different. It is a little different. Play around with it. Talk with your neighbors. We'll meet back in a minute. If you're watching this video on the road, I want you to pause it and you can resume in 4, 3, 2. These are the three options that I think people chose. They all work, just so you know, because the only goal is to get rid of the imaginary part of the denominator. If when you foiled it, you got rid of it, you're good. Which one of these is the one to pick if we're truly, truly using the conjugate? Is this number a complex number? What's A? Do we agree that this is really 0 plus 2i? And if we view it like that, what's the conjugate? Or 0 minus 2i, but you're right, it's negative 2i. This is the one that's the true conjugate stuff. It doesn't really matter which one you use, though. Personally, I like this one. I think this is the easiest, but they're all the same. Did the bulk of you guys use negative 2i? Okay. I'm going to do this one here, unless somebody wants me to do a different one more so. Okay. These are all the same, but let's see what we get. Downstairs, I get negative 4i squared. But hold on. Negative 4 times I squared. Negative 4 times negative 1. It's a 4. Everybody okay with that first step? Okay, I'm going to distribute. We get negative 6i minus 2i squared. Okay, this is going to bug me. Negative 2i squared is negative 1. Is that just 2? So I would rearrange this to be 2 minus 6i, and then everything's over 4, right? Or, if I just want to jump right now, if everything's over 4, can I just put both of these over 4 separately? Am I correct? So I didn't ask can I do more, just in general. Am I right?
Yeah.
Absolutely we're right. I'm not the most simplified form, but this answer is okay. Do we all come up with 1/2 minus 3/2 I? Okay. This is what we got with negative 2i. 2 iers. You all have 2 i's, so that's kind of cool. Did you guys get the same thing?
Yeah.
Let's check. Do we agree? Go ahead, Red.
Could we put the answer as 1 minus 3i?
You're not going to be wrong, but generally speaking, we want this form that very explicitly shows a plus bi. Now, like, if you want to test, if you want to stop here, I'm cool with it. Like, you can keep it in that form. But let's check this one. Anybody else do 2i, or is there only one? Positive 2i?
Yeah.
Okay, let's check it. My numerator is 6i plus I squared over 4i squared, or 4 times negative 1. I'm just going to call it negative 4. Cool with that? Addison, still cool? What's I squared? Plus 6i. And this gets divided by what number? Negative 4. Ooh.
The negative 1, the I times 2i.
2.
That should be 2, negative 2 right here. Because it's 2i squared, right? My bad on that. Thank you for the catch. I was wondering what happened. What's negative 2 over negative 4? 6 over negative 4 is a negative 3/2. And there's still an I. Hey, that's pretty neat. Do I need to do this one? Okay, sure. I'll not, like, they're not long problems. Denominator, negative 2. Numerator is 3i plus I squared, or I squared plus 3. Negative 1, that's my I squared, plus 3, I. Negative 1 over negative 2 is 1/2, minus 3 over 2, I. It doesn't matter which way you go. If you get a real number in the denominator in the end, you've done things correctly, unless it's by total coincidence. Okay, these ones feel all right. Okay, the last little piece, because we spent a big chunk of time the last few days doing a bunch of dividing and starting to think about factoring ideas and stuff. Let's connect back to what we were looking at. Do you guys want to take a, no, do we want a really quick brain break?
Yeah.
Okay, we're going to go like really fast, like 60 seconds. Let's go ahead and tie this all back to factoring stuff. So here we go. When we're looking at things, a few little weird pieces, and I lied, we're not going to do the factoring stuff. I was so excited for it. Last little section, we'll come back to factoring in our next section. We are going to just briefly talk about the complex solutions. What's my shorthand for solutions? SOLN. Complex solutions of quadratics. Now, there's some wonky stuff that happens when you start asking about the square root of a number. If I just ask for the square root of 25, you guys all are going to say it's what? 5. And it's natural. Like, you might try to sneak in the plus or minus if you think I'm trying to trick you, and I totally get it. But if I'm not trying to trick you, we all agree it's 5, right? Is anybody going to say negative 5 as your first go-to? Probably not. It'd be kind of strange if you did. Not strange in a bad way, just out of the norm. When we talk about square roots, we pretty much always commit to that positive unless specified otherwise. What we're talking about with those, when we use that, the positive version, we are referring to what is known as the principal root, or the principal square root. Now, all number systems are not made the same. And what I mean by that is, although the real numbers are a larger part of the complex, there are some things that happen in the real numbers, and purely the real numbers, that don't happen when we add that imaginary part. Naturally, there's little differences. For example, if I'm in the imaginary parts, if I take any two real, I'm going to bounce back to the reals. If I take any two real numbers and add them, do I get a real number? If I take any two real numbers and I multiply them, do I get a real number? If I subtract or divide, do I also get a real number? Does the same happen if I start allowing the complexes with i's in them? If I add two complex numbers, do I get a complex number? Yeah, and there's a little bit of playing around with just the words that we use, but if I add I and I get something with an I. If I subtract it, I get something with an I. We just saw with division, I get something with an I as well. Does it always happen with multiplication? No. So if we're talking about like the pure mathematics of it, and I know that if I take I times I, it's I squared, which is negative 1. And all of a sudden, it's not complex anymore. With that, there's a bigger underlying principle here called closure, where we have a set of numbers, the reals, for example. They are closed because any operations that I do keep me in the real numbers. When we jump up and add that imaginary part to the complexes, we're no longer closed. Now, that's not entirely true because even if I wind up as a real number, I'll just say, oh yeah, it's still complex, but it's plus 0i. And there's some kind of wonky stuff that happens, but there is a difference there. And I hope we can all see it. When we're looking at this, when we are dealing with square roots and stuff, principal square roots, I'm just going to say, weird that I did it that way, are positive. The positive version of it. Now, when we're looking at these, what we're going to see, we're going to do a quick example. I'm going to put one little note within our example before we do A, B, and C. We want to be able to evaluate each of the following. And we are going to be kind of blurring the line a little bit here between the imaginary complex numbers, the things with I in it, and the things without it. Because if we do it wrong, something really strange happens. And we almost ran into it yesterday, but didn't quite happen. So I'm going to leave this blank for just a second. We're going to put 3 words here. Okay, 5 words. I can count. On A, we're just going to jump right in. We have this. I want us to take the square root of negative 15 times the square root of negative 3. Immediately, does anybody remember this lovely property? Which, if you want to put it, you can, because it does work this way. If I have root A times root B, how does this work? So let's try it real quick. If I do root 2 times root 3, what does it give me? Okay, so if you guys can tell me that answer, the lack of answer here doesn't make sense anymore. This is root what? AB. Now, it works nicely here. This is our square root property. We can't add like this. They have to be the same radical. So root 2 plus root 2 to root 2. Root 2 plus root 3 is not root 5. And it's really easy to come up with a counterexample for that. They don't work with adding like this. Okay, in this situation, there is a right way and a wrong way to do it. And we're going to make the comment right at the beginning. I see 2 approaches to this problem. We could either multiply these together and then get root 45, which is not an imaginary number anymore. Do we agree with that? Okay. Or we could maybe instead try to treat it like the imaginaries first and then do the operation. Do we get the same thing? Let's check. Let's check. Let's do it with complex numbers first. I'm going to show every little step with the understanding that you guys probably won't. Can you give me a way to rewrite negative 15 so that I can think about it?
15i.
So not quite. You're close. 15i is not the same thing as negative 15.
I.
But is it? It'd be negative 1 times 15 just before. Like, there's a lot of different answers that I think are reasonable. But do you guys agree that right now I haven't changed anything? Boom. That's a negative 1. I'm trying to make it look like it. Is that the same thing as root negative 15?
Yes.
Okay. Times, could I do the similar thing for negative 3?
Yeah.
It's negative 1 times 3.
Oh.
Now, the reason that I would do this is because right now I can see something very convenient is going to happen for me. And whether or not it winds up being the same, this one it might be, but whether that's always the case, we'll find out. Anything that I could do first before I try to multiply that? Do you guys, like, if we use this property, it goes both directions. I have the square root of negative 1 times the square root of 15. Do you guys know the square root of negative 1 if I rewrote that? I. Do you guys agree that this is I root 15?
Yes.
Now, if we do the other side of it, this one is just I root 3. Everybody cool there? Okay. Now, when we commute, and I want to make this really clear, some people, and you're not wrong, and I think your book might do this, I believe your book writes this number like this. Is it any more right or wrong? No. Which one of these is going to lead to disaster down the road if you're not super duper careful? This one, because all it takes is you being a little bit too aggressive with your pen or pencil, and now it looks like we're taking a very different square root. I always move the imaginary I value out to the front every time. You should. I don't really care if you do, it's up to you, but if you make a mistake here, I'm going to say, haha, told you so. Not really. I would never say that as your teacher, just for the record. Okay. Can I arrange stuff differently? Like this times this times this times this. multiplication commutes. Is this I squared times something? Root 45. And whether or not we clean up the radical, I'm sure we will. But anything else obvious that algebra says we can do? This is a negative. And we're going to do this here. I'm going to write a -1. I will actually write it, the whole number. I want to break down 45 so that I can write it as a nice radical. Is there a square number that goes into 45?
9.
9 times what?
5.
So when we clean it up all the way, I know the square root of this one. What comes out?
3.
And it multiplies by? Do we all agree this is -3 root 5? Okay. Did we cheat anywhere? No. I do not want you to write this one. In fact, I don't want anybody to get confused about writing it, so I'm going to pause the video if you're gone for the trip. Sorry. If we had done this differently, and again, do not write this down. Don't write. I'm afraid they are just going to look at the pictures, and that's okay. But if we did it the other way, and I just tried to multiply right away, do you guys agree I'm going to get root 45? Because negative and a negative. We just magically, and it doesn't really feel like magic, there's something weirder happening. We just completely said, forget about the imaginary parts, they're not there. Were they there? Because now when we do this, we get our answer is going to be 3 root 5. Did we get the same answer? When you're doing this, whenever you have radical stuff that's going to take you into the imaginary part of the numbers, we need the following comment. Always change to the complexes first. Now, before we do any operations, we're going to change it to the complex variant. And all that that really means is we want the I stuff out of the way before we ever shove stuff together. Every time, because we see we get two very different answers. One of them gives us the principal root, which is what we found, 3 root 5, but we didn't specify. We are going to make sure that there's no ambiguity to what our answer is supposed to look like. We'll just always change with I first. All right, I want you guys to do one more for me. And then we'll have a little bit of time. Ooh, cool. I want you to take for me the square root of -27. And from this, I would like you to subtract the square root of -12. A little different, but same thing. There is an opportunity to jump to being the imaginary part of the complex numbers first. You should do that. All right, so looking at this, I have broken down this into all of its prime factors with the -1 included so that I can get the imaginary parts. Can we take out two things from this first factorization? The square root of 9 is 3. The square root of -1 is I. Do we all agree that this is 3i root 3? Minus this one, a 2i comes out, and a root 3 is left. Do these match? So it's no different than if I had 3x plus 2x, or minus 2x. Like the same idea works. We have like terms. These can combine. What's 3i minus 2i? 1i, and the only thing left? Boom. I root 3. We're done. Okay. Where this shows up, can you guys think of anything with quadratic stuff where you've seen this show up before? What sort of problems would ever, in quadratics, take you to dealing with i's? Ooh, louder?
Quadratic formula?
It's the quadratic formula. Do you guys know the quadratic formula?
Yeah.
Who does not have it memorized? Okay, so check it out. We're going to sing.
Oh.
All right, do you guys know the song Pop Goes the Weasel? Can we all agree it's but bum ba bum ba ba da da dum ba bum 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 bum. Everybody cool with that song? -b plus or minus the square root of b squared minus 4ac all over 2a. Now, I don't really remember it that way. If you're sing-songy and it helps, you can. In my head, it's much more exciting. When in my head, and the voice is different, I don't even know that there really is a voice. That's a weird thought. Here's how my thoughts go if my voices had sound. Negative b plus or minus the square root of b squared minus 4ac. Like, it's just boring and bland. I can remember it. If you can't, sing-songy always works. Do I need to write down the quadratic formula for you? If you want it, the roots of any quadratic written in the form ax squared plus bx plus c. If you are setting this equal to 0, which is what happens when you're looking for the roots, you are going to wind up with a wonderful expression at x equals negative b plus or minus the square. I don't know how they actually works there. I've never taught it like that. B squared minus 4ac all over 2a. If this piece right here, called the discriminant, if that piece is negative, you are going to have roots in the complex numbers, which means it does get to cross an axis, but it happens somewhere that we don't see it when we graph only the x and y plane and the real numbers. Okay, this weekend, you get some practice. Indeed. You get a bunch of days. I'm crazy jealous because I do not get tomorrow off. But I'll tell you, I'm going to come in much later than I normally do. And beyond that, I'm going to stay up much later than I normally do. Indeed. All right. So today we knocked out lesson 2.4.2. I'll zoom way in. I'll name the lesson here in just a minute. But our homework today, we're going to say this is homework 2.4. You guys will find this on page 152. I'm going to take out the vocab, but I'm going to ask you about the vocab just without doing stuff. Maybe not today. I want you to do 7, 11, 35, 39 through 45 odd, 51, 55, and 69. What? That was supposed to be 51, 55, 51, 55, and 69. All right. Appreciate the heck out of you guys. Go cheer on your fellow Raiders tomorrow at 6 p.m. for the swim meet. Don't be late. Yes, please leave your bell ringers on your desk. I was going to ask you to do a thing at the end, but we don't have time, so we'll hit it later. Ballers, if you're watching this before your game, I hope you won. If you're watching it after I hope you win. If you're watching it after, I hope you won. Message me if you have issues, questions, concerns. Later, Raiders.